Hello students, and welcome to this 11th lecture of the heat transfer course EEAQ 3235. Now today we're going to have a look at numerical methods of analysis of heat transfer problems. And as we know that we have quite an elaborate analytical solution and methods for solving heat transfer problems. But you find that in many practical situations, the geometry or the boundary conditions are such that the analytical solution is quite difficult or impossible. Now, with such complex situations, the numerical methods, and especially now that we have very fast computers, stands in a good state. And that is what we are going to look at. Now you find that in every physical situation or system, we look at the conservation laws, i.e. the conservation of mass, the law of conservation of momentum that gives us the second or the Newton's second law of motion, and then we have the law of conservation of energy, which is otherwise referred to as the first law of thermodynamics. And with these laws, coupled with the constitutive laws like the famous equation PV is equals to MRT, okay, stress strain relationship, we can handle any physical system problem. Now, in heat transfer, we came up with the heat diffusive equation. And there are quite a number of variations of that equation depending on our assumptions. And the first one, or the one that I would like us to look at for the sake of analysis, is the one that we came up with, that is the Laplace equation, whereby we saw that d to t by x squared plus di to t by y squared is equals to 0. So our task is to develop a scheme that can enable us to solve that equation using other numerical methods. Now we have a number of numerical methods. The first one being the finite difference method, which is the oldest, whereby we find a way of solving partial differential equation like we have in the Laplace equation. The second one is the finite element method, where the problem domain is divided into a set of finite elements which are generally unstructured, and we come up with solutions for such elements, and then we do it for the global scenario. And the last one is the finite, not really the last one, but the third example is the finite volume method, whereby now the equations that we are supposed to handle are in integral form. So now we need to have some approximation method for the first order derivatives and for the second order derivatives. So as we know, this equation here, and whether they are in partial differential form or integral form, they are continuum. And what we are looking at is what generally can be referred to as computational methods. And computers do not understand continuum. It can only understand discrete systems. So we need to break down the continuum into discrete, let us call them things that can be understood by our computers. And one of the best way to do it is to expand these equations or functions that are differentiable using the Taylor's series about some point x is equals to xi, where I stands for the initial. So we have numerical, we have now the Taylor's series, which is fx is equals to fxi plus the difference between xi and x, the first derivative, partial derivative of the function by x evaluated at our initial position plus xi minus x, or the other way around, or x minus xi squared over 2 factorial. the second derivative of the function with respect to x evaluated at I plus so on and so forth until xi minus x n over n factorial di square di n of f di x n evaluated at I plus the higher order terms h. So that is our Taylor's series. So in the neighborhood of a node or a grid point x or xi, let us use xi, we have a grid point xi plus 1 and a grid point xi minus 1. So for f x I plus 1 we have f x I plus x I plus 1 minus x I di f I di x at I plus x plus xi plus 1 minus xi squared over 2 factorial di 2 f di x at I plus higher order terms. Now this is equal to fi plus 1. Okay, f of I, the function of x at I plus 1. For xi minus 1 we have f I minus 1 is equals to f of, or it is equivalent to f x I minus 1, which is equals to f x I plus x I minus 1 minus x I df by dx at I plus x I minus 1 minus x I squared over 2 factorial die 2f die x at I plus higher order terms, and we'll call this our first equation, and that is our second equation. Now, rearranging equation 1, we take equation 1, we have df dx at I is equals to, is equals to f I plus 1 minus f I divided by, we have this multiplier for df by dx, so we'll divide through by this, so we'll have a divided by x I plus 1 minus x I, right, minus x I plus 1 minus x I over 2 because of the 2 factorial, and then we have a d squared f a dx 2 at I plus h. And this gives us what we refer to as the forward difference. A difference, the scheme denoted by FDS. So that equation can be written as df by dx at I is equals to fi plus 1 minus fi divided by delta x. Okay, you can be specific, delta xi plus o delta xi, where delta xi is equals to xi plus 1 minus xi. Now, o delta xi is called the truncation, truncation error, because I will omit this if a delta x is very small, assuming that whatever we have that is above the second or the first differential derivative, the first derivative is so small that it does or it contributes a little to the equation. So we have Similarly, we can get the backward scheme, which is df by dx at I is equals to, that is by using the second equation, equation 2, it is given by fi minus fi minus 1 over delta xi minus 1 plus o dxi, which again is the truncation error. Now, supposing we subtract equation 2 from equation 1, df by dx at I is equals to fi plus 1 I minus 1. Notice now the range between I plus 1 and I minus 1 over x I plus 1 minus x I minus 1 plus xi minus x I minus 1, all of that squared over 2 factorial x I plus 1 minus x I minus 1, and this is minus, there is a minus up here, minus x I plus 1 minus xi, and all of that is squared d squared x f dx evaluated at I, okay, at I plus h. So again, this can be written as df by dx I fi plus 1 minus fi minus 1 over x I plus 1 minus x I minus 1 plus o delta x, and this time it will be delta x squared that takes care of the second derivative part and higher derivatives parts. Now, if xi plus 1 minus xi is equals to delta x, you'll concur with me that xi plus 1 minus xi minus 1 is equals to to delta x. So our df by dx at I is equals to fi plus 1 minus fi minus 1 over 2 delta x plus the truncation error or delta x. Now we have an approximation method for the first order derivatives. Let us have a look at approximation. Of the second order derivatives. So we can say that to obtain the second derivative, we use the approximation. For the first derivative, such that d2f by dx at I is equals to df dx at I, or at I plus 1 minus df dx at I divided by xi plus 1 minus xi. So we can say that df dx squared at I is equals to f I plus 1 minus fi, because that is the derivative, first derivative, divided by x plus 1 minus xi minus fi minus fi minus 1 over x I minus x I minus 1, and all of that is divided by x I plus 1 minus x. So this is equals to fi plus 1 minus fi times this one here, xi minus xi minus 1 minus that fi minus fi minus 1 times x I plus 1 minus x I divided by x there is I there xi plus 1 minus xi, that one there, multiplied by xi minus xi minus 1, all right, and we have x I plus 1 minus x I. So essentially what I've done is trying to simplify this. So I multiplied that and that and came up with a common denominator there. So our common denominator, and then the numerator is that times that, and that times that. So that times that minus that times that, and that is what we have there. Then at the bottom here we have that multiplied by that multiplied by that. That is what we have there. So we have this is equals to fi plus 1 minus fi xi minus xi minus 1 minus fi minus fi minus 1 xi plus 1 minus xi divided by xi plus 1 minus xi, all of that squared, times xi minus xi minus 1. So we can say that for a uniform grid, we have xi plus 1 minus xi being equal to, in magnitude, to xi minus xi minus 1, and we'll call that delta x. So we have our di2 f di x squared being equal to fi plus 1 minus fi delta x minus fi minus fi minus 1 delta x divided by delta x squared times delta x. So this becomes fi plus 1 minus fi minus fi minus fi minus 1 divided by delta x squared. And we can remove the brackets, and if you remove the brackets you'll get f I plus 1 minus 2f I plus f I minus 1 over delta x. So supposing we had a look at, we have a two-dimensional body, that is a body that has dimension in the x and y direction, that is divided into equal increments in both x and y direction there. Now we have a Laplace equation there, heat equation there, and we want to use this diagram here for our analysis. So we have the major node that we are focusing on, that node there, and let us call that node M, N. So if you move in the x direction, we'll come to this node, and at that position we'll have moved 1 unit that way, so we'll have M plus 1, but we will not moved in the y direction, so we'll still be at n. So M plus 1 comma n is the position of that node. Now for this node here, we are moving up in the y direction and not in the x direction. So our x coordinate remains M, but our n coordinate, or the y coordinate, other position becomes n plus 1. For that node there, we've moved 1 unit to the left of our main node, but we've not moved in any way in the y direction. So we have n remaining the same, and then our movement is in the negative direction, so we have M minus 1 comma n as our position for this node. For this node here, we have a movement in the y direction in the negative direction, so we'll have n minus 1 there, but M are remaining the same. Now when you have heat transfer by conduction for an interior node, this one, and it is in the neighborhood of two nodes, that node and that node in the x direction, and that node and that node in the y direction, you should note that the heat transfer by conduction is half in that direction and half the amount in the opposite direction. And the heat transfer that way is a half in that direction and half in that direction. And to make things easier, we will take a region, all right, a region as shown there, shaded in yellow, that is at a halfway there, a halfway there, a halfway there, a halfway there, halfway there between the nodes. So we can now write down the equations for our first order derivatives. So di t, di x at m plus a half, because we've said we are moving a half in one direction and half in that in another direct in the other direction. So at m plus a half comma n is equals to, that is at that position between that node and that node there, is given by t m plus 1 comma n minus t m mn divided by delta x, as per the equations, approximating equations for our derivatives that we came up with. Now dt dx for, let's say, a node m minus a half comma n comma n is equals to t m comma n minus t m minus 1 comma n divided by delta x. Dt by dy, now the movement is in the y direction. We have at m n plus a half, because the movement is in the y direction. Now this is equals to t m n plus 1 minus t m n divided by delta y dt. Okay, can come here, dt by dy at m comma n minus a half is equals to t m n minus t m n minus 1 all over delta y. And then we have d2 t dx squared is equals to dt by dx m plus a half comma n minus a dt dx at m comma, okay, m minus a half, okay, minus a half minus a half comma n comma n divided by delta x squared which is equals to t m plus 1 comma n plus t m minus 1 comma n minus 2 t m n divided by delta x squared. If you refer to the equation that we got for di 2 t di x squared. Okay, so we had in the equation that we derived f I plus 1, okay, f I plus 1 minus 2f I plus f I minus 1. And if you look at this diagram here, that is our f I plus 1, this one here. This is our f I plus 1 here, and that is what we have here, and that will be our f I minus 1, this one here, which is our tm r of m minus 1 comma n minus 2f I, and this is our fi, and fi is m comma n, 2 t m n divided by delta x squared. Okay, so now let's have a look at d2 t by dy squared of m comma n, which is equals to dt by dy m n plus half m n plus a half minus dt by dy m comma n minus a half divided by delta y. And you can use the same analysis to get our equation as is equals to t m n plus 1 plus t m n minus 1 minus 2 t m n divided by delta y squared. So let us go back to our Laplace heat equation, which is di 2t by di x squared plus di 2t dy squared is equals to 0. So this becomes t m plus 1 comma n plus a t m minus 1 comma n minus a 2t m comma n divided by delta x, and we are adding di 2t di y squared, which is t m n plus 1 plus a t m n minus 1 minus a 2t m n divided by delta y squared. These are squared, and that is equals to 0. Now we will have some simplifying assumption that a delta x is equals to a delta y. So if that is the case, then you can multiply through by delta x, which is equal delta x squared, which is equals to delta y squared, and you will get t m plus 1 comma n plus a t m minus 1 comma n plus t m n plus 1 plus t m comma n minus 1 minus 4 t m comma n is equals to 0. Okay, and if there is heat generation, the equation can be written as Tm plus 1 comma n plus Tm minus 1 comma n minus 2 Tm n over delta x squared plus Tm n plus 1 plus Tm n minus 1 minus 2 Tm n over delta y squared plus a q dot, if you can remember, r over k, and that is equals to 0, where q dot is the rate of heat generation per unit area per unit time, and K is the conductivity of our material. Again, when delta x is equals to delta y, this becomes a Tm plus 1 comma n plus a T m minus 1 comma n plus, okay, a T m n plus 1 plus T m n minus 1 minus 4, okay, yes, plus q dot delta x or y squared, delta x squared over k minus 4 tmn is equals to 0. Let us have a look at an example of a plate that has been divided into elements as shown, or a mesh, and we have some 1, 2, 3, 4 nodes, and we're told that that surface there is at 500 degrees, this surface is at 100, that surface is at 100, and that surface is at 100. And we will use this equation that we've developed to come up with the temperature distribution for the 4 nodes. So now let's have a look at node 1. So for node 1 we have, this is our node here, node 1, and if we move to the right we will go to node 2. all right, if you go to the left you go to this surface that is at 100. If you go up you go to this surface that is at 500, and if you go down from node 1 you go to T3. all right, so if you move that way, that is Tm minus 1n here. all right, you'll go to the surface that is at 100 degrees, and from that node if you go up, that is Tmn plus 1 here, you go to the 500 degrees. all right, so Tm n plus 1, that is that position there, is 500 degrees, plus, if you go to the right of this node you go to T2, and if you go down you go to T3, and we'll subtract 4 Tmn. so this is the Mn node, okay, so this will be 4 T1, and that is equals to 0. For node 2 we'll have, this is now our node, and from node 2 if you go to your left you go to T1, if you go up, that is to Tmn plus 1, you go to 500. If you go to the right you go to the 100 degrees, and if you go down you go to the T4, the node that is at T4, and we are subtracting 4 Tmn, and Tmn is a T2, so for T2, which is equals to 0. Then for node 3 we have going to the left, you go to the 100 degrees temperature. Going to the right, you go to T4. All right. Going down again, you go to 100 degrees. Going up, you go to T2. And we are subtracting 43, which is equals to 0. For node 4, we have going to the right, you go to 100 degrees. Going to the left, you go to T3. Going up, you go to T2. Going down, you go to 100. 100. This is not T2 but T1. This is T1. $100. Okay. And we are subtracting for T4, which is equals to 0. So now we've come up with 4 simultaneous equations with 4 unknowns. And because we have the minimum, the bare minimum of the number of simultaneous equations are required to solve for 4 variables, it means that this set of equation is solvable for T1, T2, T3, and T4 by the usual elimination methods, and so on and so forth. But if you go back to our diagram, this diagram here, you can see there is some kind of symmetry. Okay, so T4 or node 4 surrounded by an environment, 100 there, T3 by 100 and 100, so that implies some kind of symmetry. T2 is surrounded by 100, 500, T2 by 100, 500. So there is whatever is symmetrical, and we can deduce that then T3 will have to be equal to T4 and T2 will be equal to T1. So we have from symmetry T2 is equals to T1 and T3 is equals to. So we can take the equation, this one, T3 plus T2, that is plus 100 plus 100, that is the last equation, minus 44 is equals to 0. And we have seen that T3 and T4 are the same, so we can write this as T2, that is this T2 here, plus plus 200, that is 100 plus 100. This can be written as T3. So T3 minus 43 is 3T3, and that is equals to, okay, and then we can take the first equation, whereby we had 100 plus 500, so that becomes 600, plus T2 plus T3 minus, instead of 41 we'll put 42, is equals to 0. So 600 plus T3 minus 3T2 is equals to, and now we have two simultaneous equations, that one and that one, that has a T2 and a T3, and if you solve those two simultaneous equations, you will get a T2 is equals to 250 degrees, which is also equals to T1, and you'll get T3 is equals to 150 degrees, which is also equal to T4. So now you have your temperature distributions for the nodes. You can go ahead and calculate the heat flows, and the heat flows Q is equals to the sum of, from the Fourier's equation, K delta X or delta Y, depending on your movement, delta T divided by delta Y. So it can be that, or K delta Y delta T delta X. So let us have a look at the 500 degrees C phase. Okay, if we go back to the diagram, let's have a look at this phase here, and this phase is in direct communication only with node 1 and node 2, which both are at 250 degrees. So the heat flow there will be Q is equals to minus, note that for this case we are moving in the Y direction from node 2 to the face, 500 degrees, node 3 to the node 1 to the face, and node 2 to the face, which is a vertical motion. So our equation will be minus K delta Y delta x, then we have both of them are at 250, so the sum will be the sum of the two, that is 250 minus 50, 250 minus 50. And if delta y is equals to delta x, q becomes minus k times 250 plus 250 is 500, so this is equals to minus 500 k. So let us go to the 100 degrees C faces. Again, let us go to the diagram, and you can see if we have that face, and that face that are at 100 degrees C. So this phase is in direct communication with node 1 and node 3. That phase is in direct communication with node 3 and node 4. And this phase is in direct interaction with node 2 and node 4. Okay. So node 3 and node 4 all are at 150 degrees. So we will have 150 degrees minus 100, 2 times that one and that one. Okay, that is when interacting with this wall, and that one and that one when interacting with this wall, and that one and that one when interacting with that. So we'll have 150 minus 100. And these are at 250 degrees. So we'll have 250 minus 100. This one with that one with that. So that will be 2 times. So we'll have Q is equals to minus K delta Y by delta X, 250 plus, let us put a big bracket there, plus 150 minus 100 plus 150 minus 100 plus 150 minus 100 plus, we've said there will be 4 of them, 150 minus 100 plus 250, because we have seen 250 minus 100 will be 2, and if the delta X is equals to delta Y, then that will give us 500 minus 500 K, which is as we had for the case of the 500 degrees.